Gang, welcome back to the channel. The topic du jour is none other than the very well-known Sony TAN-8550 v-fet amplifier from the 1970s. For those of you hi-fi aficionados out there, this unit needs no introduction. This is a very good sounding amp, and that's why it's well known. It is actually one of the best sounding amps most of us will ever hear. But these are 50 years old now, and we cannot use them with any sense of reliability. Therefore, we must do some tender loving care. We must help them survive. And that's exactly what I'm trying to do, help survive as many as possible. If you watch my channel, you see that's basically what my channel is mostly about, working with v-fet amplifiers. v-fet stands for vertical field effect transistors, also known as a SIT, static induction transistors. These, in my opinion, and others, are some of the best devices ever invented for audio, and Sony made very good use of them in the 1970s. But again, while some of these are still working, as they are 50 years old, which is a testament to the build quality of these amplifiers, they do need to a full go over for them to work reliably. And this is what this video is about. About a couple of years, maybe even older than that, I started thinking on how can I make this amplifier work at least as good as I did when it left the factory. And I had a few runs into trying different things, and I kind of put it aside until about, I would say about a year ago. And then it took many months of iterative progress to get my goal to fruition. And again, as I said, the goal is to get this amplifier to work at least as good as new. But I think I went well beyond that. So this is not a restoration video. It is restoration in its common sense, means bring something old to its original condition, or bring something broken to its original condition. And by the way, it kind of lost its meaning. It's being loosely used these days. So this is not a restoration video. It goes well beyond that. It's something that I'm trying to think that if Sony would have made an MKII, they would have incorporated some of these changes that I'm about to share with you that I've done to this unit. In other words, it's an evolutionary progress for this amplifier. Some of the changes that I'm making are foundational, there's no criticism to the Sony engineers. I just want to make that disclaimer. I have utmost admiration for what they created. This is a masterpiece. But 50 years ago, they didn't have access to 50 years worth of data, which we have today, which affords us to play Monday morning quarterback to say, you should have done this, you should have done that. Plus, we have a lot more, we have a bunch of technological advancements since then, which I plan to actually put to good use. And so that said, this video is not a restoration video. It is essentially an evolutionary type of progress that I envision Sony would have done to bring these amplifiers to their next version, per se, right? It's a version upgrade, basically. So that's what this is. This tackles core features, core functions of this amplifier, even though it looks like it's still in its original shape. Case, all major buttons and switches, etc. And the unit that you're seeing in front of you right now, it's actually a complete unit. All the work that I intended to do to this amplifier has been complete. This actually isn't my unit, is a European version. It belongs to someone else that's actually a collector, has multiple v-fet amplifier, including one just like this, with all the changes made to it, and additional units that are either rebuilt differently or have been in original condition. And so what I can tell you that through my project, I didn't just achieve to change things and make this thing reliable and improving it, in terms of reliability and functionality, but also in sound performance, which is not easy because this already sound very freaking good. But I tell you right now, if you did have the opportunity to listen to one of these amplifiers in the past, you haven't heard one working at its full potential in terms of sound quality. I will leave it at that, and kind of that's exactly what I'm going to say about, all I'm going to say about sound quality. It's just that sounds very freaking good, better than it sounded when you, works better than when you left the factory. That's about the description I can give you in a very summarized way. Now, for this video, what we're going to do is a few different things also than what we've done in the past. In the past, I would have walked you guys through different stages of the work done for a single unit. What we're going to do right now is we're going to walk you through different stages of multiple units that are in progress, basically. And this being fully complete, we're going to be essentially coming back to it at the end to kind of show you guys how everything fits and works together inside, right? This, again, as I mentioned to you, actually works. You're not seeing that VU-meter right now very clearly because the light in the room here is kind of makes the light, like those light beams, kind of dim. But for those of you that are not aware what this is essentially a fully analog VU-meter, and it uses a light bulb and a set of mirrors to project those two beams on this display here, which is not digital. It's just a simple display. And that's all I'm going to actually talk about when it comes to this VU-meter. There are a lot more sexier topics inside here that I will talk to you, but I wanted to kind of briefly show you how this thing looks powered up. One other thing, this will be a very lengthy video because there's quite a bit of variety of subjects that I will try to touch upon, and I have to be very cautious from a time perspective vis-a-vis the level of details I can provide for each one of those topics. So I don't want to be very shallow, but I can't go into much resolution, too much depth for each of the topics. Otherwise, this is going to be likely well over an hour video. So I'm hoping to keep you guys entertained for the entire duration. All right, so what we're gonna do right now, again, this is where we're gonna come back towards the end, towards this unit, which is complete. But now we're gonna go straight back to the beginning and talk about this other guy right here, which is actually fully original condition. Nothing's been done to it. It's more or less not even cleaned, okay? So I'll get my chair and I'll be right back. All right, so this is a unit, as I mentioned to you, that hasn't even been cleaned, fully original. So the goal here is to first walk you guys through the all the functions on the front panel. Then we're going to pop the cover. We're gonna give you the lay of the land, description of the major modules that comprise this amplifier. Then we're going to open up some schematics, look at some of the changes to the circuits that I have done here, and then we're gonna look at actual units that are open where the work is in progress, then go back to this guy right here. So again, very ambitious timeline here. I have my muse right here, nothing better than some red California wine to keep me entertained here. Hopefully I can speak coherently by the time we end the video. Baby, I'm hoping to still be able to articulate my ideas, express my ideas coherently. Okay, so let's start with the let me move this a little bit. I have to excuse my videographer skills, which suck royally. So again, I'm not going to talk too much about this VU-meter. There's not much I'm going to do to it other than replace its bulb. You saw it on the other unit over there powered up. This right here also uses a incandescent light bulb. This I will actually replace with an LED. This I actually have to leave as a light bulb. There's a way to make this work with LEDs, but requires an array of LEDs to cover all the functions that just one light bulb is capable of doing. It's a different project I may end up working on at some point in the future, but it's not on my priority list. It is really very little value from that because this works just fine with the light bulbs. Those light bulbs last a long time and they're not obsolete. You could pick them up from any store these days. Like they're very the availability is not an issue. So very little yield from the work to convert this to LEDs. All right, so that's all I'm going to talk about this VU-meter. Okay, let's focus on this lower section right here, which is a lot more important actually. This is a speaker selector. The Sony TAN-8550 has 3 sets of speakers. What do you call this? The speaker set A, speaker set B, and there is a speaker set C or direct, which is actually only in the back. It's not switchable through here. It's not selectable through here. That is also called direct out. And there are a couple of very critical reasons why we must address this the right way. First of all, I believe this is an obsolete function in terms of what you would find today in a modern amplifier. But since it is part of the original unit, I want it to remain functional, so I'm not going to cancel it out. And if I'm going to let it be functional, then I want to make sure that works really well, better than new. Again, that's the goal. The goal is to make it reliable and working better than new by making use of 50 years worth of data and new technology that we have available today. So here's the problems with this speaker selector. The contacts inside the selector are open to air contacts. Here is essentially one of the selectors right here. It has 3 waffles, 1, 2, and 3. The front waffle, actually, what it does is switches input signal so that we have a level adjustment available when we're using speaker set B. The reason for that is essentially this is a speaker sensitivity adjustment. If you had to compare 2 sets of speakers, let's say speaker set A and speaker set B, and you want to do a side-by-side comparison, you're going to hear the differences in the quality of the speaker, but cancel out the sensitivity between the two. You would probably wanted to use one hooked up to B, and then essentially either increase its gain for that. Let's say if it's a lower sensitivity speaker, or vice versa, etc. So now that said, because this handles because of this volume, the input signal of the amplifier travels through this waffle right here in the front. And as I mentioned to you, this waffle uses contacts, which if you see in here, this have been cleaned, so they look really nice, but they typically oxidize, and they don't look as nice after a few decades, right? So this is a 50-year-old amp, so you could see that, you know, I don't have one that's dirty here because this one is being cleaned, but they don't look like this, right? The other 2 waffles in the back, they switch the output to the speaker. So essentially this will switch between speaker A, speaker B, speaker set A, speaker set B, and that's fine because really not so many people will use this function. As I mentioned to you, it's more or less an obsolete function, and so I'm not to worry about that because we do have a direct out, which also has its own problems, but we're going to touch upon that in a second. But I think the goal here is for me to essentially, instead of redoing this entire board, which as I mentioned to you would be would not yield many benefits, right? It would be not be beneficial for me to do this entire board, but I do want to address the front end of the selector, which is the input signal. So for me to do that, I have to essentially offload this function to a relay, which I'm going to do to hijack the the engagement of this potentiometer on and off, because that's all this thing does. It's either putting this potentiometer in the signal path or bypassing the potentiometer. That's all it does. And we could handle this by using a relay without having to redo this entire board, which essentially would not be feasible considering the value we're getting in return. Other than that, here is the toggle switch assembly that you're seeing over here. All this does is essentially it's a V-meter sensitivity adjustment. If you're playing music at very low levels, you're not going to get much movement in the V-meter. So you don't want to be in 1x, you want to go into 1/10x so you could actually see the V-meter. The one other thing I would say is that this V-meter, while it is extremely fast, it's extremely nice to look at. It was very expensive to build. Sony only used it in a few models. it's also not very accurate. Only has one adjustment at the 100 watt per channel mark, and so when it works below that or above that, it is not as accurate. It's definitely not as accurate as for example, the Yamaha analog dial meters, which have at least like 4 different adjustments. The C1 has 4 different adjustments, B2 has 4 different adjustments, and the UC1 has 3 different adjustments. So it's much more precise across the entire dial from 0 all the way to about 150 watts. Very precise. This one it's actually very fast and very cool to look at, but it's not very precise. Again, I said I wasn't going to say anything about the meter, but again, that was, I think, the last thing I will say. All right, so we talked about this selector. Why we're going to improve this by using a low-level sealed relay to hijack essentially the input function, because this handles all the input signal at all times. So basically the way this works is you coming, I'll show you when this thing is open. The input signal comes from the RCA here on the back, and it kind of goes in all the way here in the front, and then it goes from here to the input of the amplifier board. I will show you that one more time when I have this open. But in other words, at all times the input signal integrity is essentially dependent on the proper functionality of this waffle right here in the old configuration. So any type of signal degradation, any type of resistance building in here, your input will suffer. It doesn't matter whether you use this selector or not, whether you use this or not, right? So keep that in mind. That's why I mentioned to you, some of these changes are going to be foundational in nature. So we're essentially applying, keeping the function, but applying modern solutions to address this. Again, for this, kind of went back, but for this selector right here, the only thing I'm going to do, because it only handles the meter, so it's not a critical function. The only thing I'm going to do is I clean them. This one, it's already clean. You could see in there. You could actually see up on the screen how one switch that's being taken apart. This is kind of like, and I should have mentioned this. This is kind of a waste here, because maybe something I may do in the future. But if you notice, it's only one switch is actually doing any contact. This is kind of free in the air. All it does is act as a toggle. So basically, only the front contacts and the rear contacts of the switch are being used. So what I've done in the past to resolve some of these issues with this type of switches, when let's say this one was not fully repairable anymore, even after being cleaned, was having issues. Essentially, I used some wires to in crisscross wires in here essentially. So I created basically redundancy of the contacts between the two switches, and so that alleviates the problem for a long time. I may do something like that for this, not for this units here, because this worked correctly. I already tested all the switches, but as a kit to basically drop in for for others that may have issues with their switches, because this is definitely a difficult switch to find. There is ways to do this without this switch, but again, it's too much work. So it's better to give the original one work, and that's it. All right, so this kind of ends my high-level description of this side right here. Let's move to the right side. Here we have actually more critical functions, and both of these need to be addressed. First, we'll talk about the potentiometers here. These potentiometers are generic standard. They are 20 millimeter length shaft, 6 millimeter in diameter neural shaft, and 100 kilo ohms, and these are linear pots. And let me see if I have one in here. They look kind of like this, so very generic. They're made by Alps, and you have three choices actually when addressing this. A, clean the original ones, given that they are not broken. If the retainer is broken, you need to do something with them. You need to throw them up, basically replace them. And then you can replace them with two different type of pots, either new old stock such as these, or there are drop-in replacements that are made brand new today by Borns and other companies that will fit right in here. The problem is, what I found is that the quality of the original pot, this one right here, if you just clean it, it's much better than those that are brand new made today. Those are just pure junk. The retainer is garbage. You pop the knob in here once or twice and the whole shaft pulls out. It's just horrible quality. So these original ones, if the retainer isn't broken, you could reuse if you know how to clean them properly. But if you don't and you have access to new all stock pots, you replace them. This is actually what I'm doing to these units right now. I'm replacing all this old pots with the new all stock because I'm lazy. I don't want to clean them. Plus, these ones right here, I think they're better quality. They are ALFs, but I think a newer version. The feather that attaches the what do you call that? The carbon. It's actually on this pot, the original ones, it's split in two. So you have 2 points of contact. In this one, the feather, same feather, is split in 4, so you have more redundancy of contact. So what that means lower noise, lower scratchiness, because it's really hard to lose contact on all 4 points at the same time. And here you have twice as many contacts, so it's a better pot altogether. So that's what you could do about that, other than bypassing them. But as I mentioned to you, I don't want to bypass them because I want to keep all the functions of this amplifier. Another thing you could do, actually, you could use this ones as, let's say, a balance if you want to use an output directly from a CD player or something, and then set this on speaker set B and use this potentiometer as a main control. Now, ideally, you wouldn't be using that because you could have essentially set all these things all the way up and use a preamp. That way you have one less potentiometer in a signal pot. But that's, I guess, one use of this function right here, is use this as your main pot, and essentially allows you then to have a balance between these two. So while this is not an integrated amplifier, you could actually have the balance and master level control if you want to use it that way. Again, so that's just, I guess, a perk that you could think of. The other thing we have here is these two switches. These two switches are very similar to these. I will show you them when we open the hood. Essentially toggle between input 1 and input 2 in the back, and they're kind of the same configuration as the one you just saw, where only one of the switches is actually used and the other one is just used for toggle. But that's it. So this is the front of the amplifier and its main functions. Now let me pop the cover on this amp, and we're gonna go over the guts and what everything does. Be right back. All right, here she is with the top off. As I mentioned to you, this is a Class AB amplifier. It is not a dual mono. It shares its power supply and transistor. And transformer for both channels. Here is the Class A amp section. A couple of stages on the amplification chain. It uses a dual JFET at the input for the input differential pair, 2SK58, which they're not necessarily problematic. They're quite reliable, but if they are problematic, they could be replaced with either new old stock, which is available in some circles, or an adapter could be made, and a more modern part, let's say an LSK part from linear systems, could be used, etc. There are a bunch of components in here that will have to be replaced for various reasons. Again, I am not a big fan of shotgunning. Everything shotgunning means just kind of replacing components indiscriminately. I have very specific reasons why I will be replacing a bunch of components in here. Examples of that would be components with black legs, oxidated legs, this type of fusible resistors right here, which are used quite widely in the Sonys and are known, not as much in this model. I haven't found too many bad, but in other models like the TAN-8550, they use similar type of resistors, and those drift quite a bit. What else? There are about 3 different versions of this board, so if you're working on this amplifier, you need to upgrade to the latest version. I don't know if that's been widely communicated in any service bulletin by Sony, but that's a topic for a different video. What else? On this side of this board right here, we're seeing a regulated power supply. It's essentially an 8-volt regulated power supply that feeds the light bulb inside this voltmeter. and inside this power light right here, which we said we're going to replace with an LED. Here is the power modules, essentially the individual power boards, driver boards essentially. The VFETs are on the bottom, hooked onto those aluminum heat sinks. This is the right channel, this is the left channel. These chimneys right here play a very critical role. They are essentially accelerators. They're supposed to create a convection for the hot air to rise. So very critical is that you don't cover this with anything or don't block the bottom of the amplifier, either taking the feet off or putting it on high carpet. So you cannot obstruct the air circulation on this at all. Just for kicks, for reference, these amplifiers have 3 sets of VFETs per channel, 3 pairs of VFETs per channel. So 6 total VFETs for each one of these amplifiers. They are set in a push-pull configuration, essentially 3 P channels versus 3 N channels. Each one of those transistors at idle dissipates around 11 watts per transistor, total of 66 to 70 watts. That's a very respectful 70 watts of dissipation at idle, and goes only up from there. So instead of making bigger heat sinks and a bigger amplifier, Sony opted for these accelerators here, these chimneys. So they cannot be obstructed if you love your amplifier or whatever you're putting on top of it, because that's a death sentence for this amp. They run very hot as is without anything on top, because they have to circulate that air, and it's a good thing. VFETs like to be working hot, but the rest of the ancillary components don't. And so if you're covering this up, you will likely kill the amp and whatever you're putting on top of it, because you will get baked. So I may repeat this a few times. This is a amplifier that runs really hot, maybe not B1 hot, but very hot, and the airflow circulation cannot be blocked. I also see people putting fans on this. That's cheesy. I don't like it. First of all, it looks ugly, and it doesn't do much. Like, this is not a computer. You'll be fine. Just don't put something on top of it. Don't put this inside a shelf or a cabinet, closed cabinet, and it will work fine as designed. All right. Couple of more details on these driver boards. As I mentioned to you here, there's this board has about 3 different versions, so it has to be updated to the latest version. This board's right here, and we'll go look at the schematic, but I'm just going to give you guys the highlights. Sony chose a crowbar circuit for their DC sensing, DC protection circuit. So in the situation where, in a scenario where DC is potential is detected on the output, in order to protect the speakers, the crowbar circuit gets activated via essentially it's an SCR, a thyristor that essentially shorts the output of the amplifier to ground. In such instances, the survivability, I think that that muse right here, it's saying it's has it say right now, because I'm having a challenge getting out with a coherent message, but its survivability is jeopardized, right? Because it is highly unlikely the VFETs, at least not all of them, will survive such an event, depending on which side of the sine wave this is clamping down on, a plus or minus. So that could affect all of them or some of them, and it's not a good thing. And this maybe was okay when Sony came out to this, when they were actually making buckets of these transistors, and it was an easy fix for them to take it back on the service center and just replace a bunch of VFETs instead of killing the speakers. But in later models, as you will see, they realize that's not a good thing. So they used this design for the TAN-8550 for this guy, and for the integrated version, the 8650. And we're going to address that, and I'm going to share with you how I'm going to address it when we're going to pull out the schematic. So hold that thought there for a second. Now, the other major area of concern in here is this dual capacitor. And why is that? These are actually really good capacitors that were made for audio, and some of them are still within spec. But if we are serious about having sustained reliability for many years for this amplifier, we can't be rationally leaving this capacitor in here and do all that work, right? Just because we can't find a dual capacitor replacement, because these are no longer made. Now, two things about these capacitors. The reason Sony and Yamaha for B1 and others use these dual capacitors was to manage some of the parasitic elements that have to do with capacitors, which are unwanted inductance, unwanted series resistance, etc. Unfortunately, these capacitors are no longer made and they have their own problems. If you've seen my B1 video, you know what I'm talking about. So we need to replace this for having reliability, but we can't replace it with something that would affect sound quality. So we have to figure out a way to manage those parasitic elements that I just talked about. And so far, all the replacements I have seen, they're essentially compromises or desperate measures. In other words, if it is between having a unit that doesn't work and one that works, or one that doesn't work or works suboptimal versus that one that doesn't work, you will take the one that works or works suboptimal than the one that doesn't work at all. In other words, we need to find a solution that's different than what you guys have seen to date to make sure that when we're putting a replacement in here, in this power supply assembly, will actually either work the same as good as new or better than what we have here today. And that is not necessarily just from the reliability perspective. As I mentioned to you, from a reliability perspective, you could throw a couple of new capacitors in here and the amp will work. Will it work to its potential? I'm going to tell you right now, absolutely not. At least not on your conventional off-the-shelf, skinny computer grade capacitors, which you would be able to fit within here, which I've seen a few options of. Again, nothing against those people that did that. I mean, they didn't have a choice. So I'm not condoning. I'm not condemning any of those efforts. I think it's a choice and it was a compromise that some were willing to make, but I'm not going to make that compromise. So we have to rethink this entire assembly here, and you'll see how I accomplish that when I'm going to share with you essentially the next amplifier. What else? Obviously, we're going to have to address some of the things at the back of the amplifier, which I'm briefly going to touch upon. The speaker post, the power cord is going to be removed, and we're going to use an IEC connector and input section as well. So a bunch of ancillary work, but all important nonetheless. Okay, so this kind of gives us the lay of the land, some of the description of the work that I'm going to do on this, or I'm about to share with you that I've done to some of the other units. And now what I'm going to do, I'm going to put a pause here and I'm going to pull the schematics so we could look a little bit at the circuit, at the overall description of the circuit of this amplifier and the areas of interest for me, which will be essentially which will be related to the changes that I made. All right, so let's take a look at the schematic of the 8550 amplifier. And let's start by first looking at, let's see, what else? What should we look at? Let's start looking at the selector here, the speaker selector, which is the first thing we actually talked about at the front of the amplifier. And let's look, see if I could position this camera in a way that you guys can see, and I don't shake it too much because I'm horrible, as I mentioned to you, when it comes to my videography skills. Let's see, I think this will work. All right, so as we talked about, and you will see when we turn these units around, there are three sets of speaker posts, A, B, and C, which I mentioned to you is direct. So it's direct because you could see it comes this way, and you are coming straight from the output of the amplifier. There's actually nothing in the signal path. So besides using a crowbar circuit protection, there's nothing in the signal pad that will stop the pop in the speakers during power up, which results from inrush current. Before all the current stabilized, most amplifiers will produce a pop. If you have one of the more traditional, which is more mainstream protection circuits, which involves a relay, you will have the time delay in there that will prevent that relay from making contact immediately, allows the currents to settle, then it connects your speakers. Now that pop could be nothing if your speakers are not of high efficiency, but could be very annoying if you have high efficiency speakers, and in some cases may potentially damage speakers. So along the process of reassessing crowbar protection circuit, or for lack of better words, as my genius friend Zelsko Nastasic, the head engineer from Electron Audio in Zagreb, Croatia, which is actually my inspirational muse and long-term friend and mentor, that actually brought up this topic to my attention back in a while ago when I was exploring the improvements I wanted to make to the Sony TAN-8550. He mentioned to me that this is not even a protection, it's the lack of protection that we need to be worried about, because the crowbar, it protects the speakers, but it doesn't protect this beautiful VFETs here, which again may have been a choice back in the day, but it's definitely an issue now because these things are unobtainium. So Zelshko, if you watch this video, thank you, my friend. I could not have done this without you. But yeah, let's get back to this. So if we're looking at this direct out, we also, by addressing the crowbar's protection circuit, we're also going to be addressing this issue right here with a pop in the speaker. So here's how the circuit looks like. Here's the SCR, which essentially, when it's triggered, actually allows a one-way direction connection for the output of the amplifier to be shorted directly to ground. That's a big no-no, as I mentioned. So to keep things into a Sony spirit, and to essentially think that this would have been implemented if there was such a thing as a Sony TAN-8550 MKII. I'm thinking Sony engineers would have probably used a protection circuit as the one they used in the younger sibling of the 8550, which is the 5550, which only came out about a year or so later after the 8550. I guess that what happened is they realized that losing VFETs, even when they made buckets of them, wasn't really a cool thing. So what they did with this amplifier, essentially, you no longer see the crowbar here. What you see is just the overcurrent protection, which is kind of very similar to the one that's in the 8550, but the crowbar circuit is done. It's out. What they've done instead, they planted a relay at the output, and this actually uses a time delay. This is the circuit right here. This section right here is essentially the DC protection, which triggers, disconnects that relay. This right here is essentially a time delay circuit, and these are the driver transistors for the coil of that relay. Let me zoom this in a little bit more to see if it helps. So that's what this does. So this quite a little bit more involved in this circuit. This could have been done with an IEC or something else, or a different schematic. But again, I wanted to keep things Sony, so keep it in the idea of the MK2. Here's something that senses a circuit that senses changes, abrupt changes in the gate voltage. So also, if there's something drastic happening to gate voltage, this will also be disconnected immediately. But as you could imagine, this was not necessarily like a drop in. We see the for example, the rail voltage is here 53 volts, and the gate voltage being 82 volts. The 8550 values will vary, so some adjustments needed to be made to the circuit, and it functions really well. So what we gain right now, it's not just a more modern protection circuit that we could now use direct C out. Essentially, we could use this out direct out, without the worry of running it through this pesky selector, or with a worry about getting a pop in the speakers, right? And as I mentioned to you, yes, the voltage rails are at 60 volts here, actually running about 63, 65 volts, and the gate voltage is at 88 volts. All right, so that's the protection circuit. Let's talk about power supply right now, and why is it very important to get it right. And I'm going to try to keep this at a very high level, and it may be a little bit controversial, so some people view this a little different. So if you have criticism, please say it. All criticism, it's welcome. But here's how I see this, and why I think that the power supply is so critical. Here's the dual capacitor that we need to address, to replace. And if you see, each one of these capacitors sits between ground and each one of the each rail each rail for the VFETs, essentially positive and negative rail, essentially the VDS of the unit, either 60 volts or plus or minus. And we're seeing that in the schematic right here. All right, I'm hoping you're tracking so far. So essentially the capacitor sits between this rail and the ground, which is right here. Each one of them sits between this rail and the ground. This is laid out a little weird the way Sony has it. Usually amplifiers, they run the ground right next to the output, so you kind of get that mirror look, also the, you know, reference to the ground. So if you think about this, what we are listening to when we're listening to the amplifier, this is the output of the amplifier. This is the voltage, the main, the positive rail. And here's just one transistor that separates the positive rail from the output. And these are depletion devices, so they're on at all times. Obviously, we can't keep them on because they'll fry immediately, but let's assume that this would be on. This essentially would be a straight wire all the way to this resistor, which is only 0.47 ohm. In other words, if you put a wire across this right here and you take this VFET out, or you make it so it doesn't die, what you're actually hearing is the 60 volts DC coming out of the amplifier. Of course, you're going to say you can't hear this, you will kill your speakers, etc. That's a crazy idea. It is 60 volts DC modulated with the help of this output transistors. That's all you're hearing. Every time you're listening to music, you're not hearing the input signal. You're actually hearing the voltage rails of the amplifier modulated with the help of the input signal and the different stages of the amplifier. So yes, these are very important. The fact that we're actually leveraging some of the best devices ever invented for audio, actually the best devices ever invented for audio, also helps. But you're in essence listening to the plus and minus voltage rails of the amplifier modulated with the help of these output transistors. Obviously, one side modulates the upper sine and the other one, the bottom section of the sine. So essentially, you're going to get a sine wave. Obviously, this section, as I mentioned, very important. Will manage the frequency, response, the quality, etc. But the power supply section is almost just as important as is the amplification, well, which is not really amplification station, which is the amplifier section of the entire unit. So again, emphasis on the power supply. It's not a trivial thing. You can't just throw a couple of caps in there and a rectifier and say, okay, this is going to work. I don't care. It's good enough, right? That's why I am a stickler when it comes to power supplies, and I wasn't going to just throw a couple of caps in there and rely on making just all the great changes on the amplifier section, but kind of disregard the power supply. And so this all is paying off because, as I mentioned to you, the results are quite favorable. The feedback so far on this amplifier, the way it sounds, is quite favorable, and has a lot to do with the changes that I made to power supply, which you will see in a minute. Before we go and get rid of the paperwork here, I will go over one more topic, which is the VFET ranks. And a lot of people talk about different ranks which are available in these amplifiers, it's about 6 of them in total, anywhere from rank 3 all the way to rank 8. First, let me just say something general. Don't worry about the rank VFET that you have in your amplifier. Any of these ranks in here works perfectly for this application. You will not hear a difference between any of these ranks under this application. So if you have if your unit has any of these ranks, will more than meet and exceed the specifications of the amplifier. So I'm hoping to settle that. Now, a little bit more details on what this ranks means. Essentially, this rank 3, 4, 5. Ignore the 5. Just the last digit is what matters. That is the rank. The 5 just tells us that this is our first generation VFETs. The second digit tells us the actual rank. And it has to do with the amount of gate voltage required to conduct a certain amount of current. In this case, the current that's being conducted at idle, which is what this chart is essentially based off of. The current at idle, which is it's essentially the current going through this transistor right here, and this other one, and this other one is essentially the current that goes through this through these two resistors, which are actually in parallel. It's interesting that you have three transistors, but only two source resistors for the bank. But nonetheless, that's not any kind of importance right now. The way you may have heard me calculate this currents, it's very simple. You essentially look at the voltage drop across this resistors, which is essentially the bias voltage for this amplifier is 125 millivolts, and you look at this resistors being in parallel, so it's actually you have to measure 125 millivolts drop across a 0.235 ohm resistor, and there is your current, which is about 177 milliamps, essentially IDS, the current between drain and source. They go across this each transistor. Essentially, it's I'm sorry, I should take that back. So if you do the drop of voltage of 125 millivolts across the 0.35 resistor, that will give you the total current across all three. So you have to divide that by 3 to understand what the current is for each one of these transistors. So that's kind of like high level how you could figure out the IDS current that's expected to go across this transistor. And this is also how I calculated the wattage dissipation, the heat dissipation required at idle, which is that current times the voltage, which is 60 volts VDS. Okay, so that's kind of high level. You may do that in a written on a paper at some point, and you could also watch some of my v-fet videos. But here's why I'm mentioning that, and going back to the ranks. Sony tells us because there's such a wide range of required voltage at the gate to conduct that 177 milliamps for these transistors at idle, Sony actually put in different sets of resistors in the bias circuit to make sure that we're getting the range required where that v-fet is actually can be biased successfully. And this is the ranges for the bias voltage depending on these resistors matching these ranks essentially. And you could see within this each spread here is about 2.5 volt spread starting from this one all the way here. It's about 2.5 volts across, which means that if your v-fets require anywhere between 0 and 2.5 volts at the gate, they could be matched as a set. Now, sometimes you could find a high, let's say a high 3 to be working very closely with the rest of the rank 4 and could be made to work, not a problem. Anyways, the reason I'm mentioning this to you, it's what I'm about to share with you right now. It's essentially another area of opportunity that we can tackle if we work on this amplifier. Be right back, show you something. Move this up a little bit, and let's look at this chart right here, which I have made. So essentially this amplifier that we are working on top of right now, which I mentioned is complete. These are the actual tests. Basically, this is the v-fet test that I've done to make sure that they work correctly, plus then that they are within the same rank. These are all original v-fets, so I had no worries. None of it was changed. It was apparent that they're all original. But this is how they're matched by factory. Again, Sony had buckets of these transistors. They would just go in, pick up some from the rank that was matching, and they would throw them together. Didn't pay attention too much on matching them any farther than that. So for them, 2.5 volts was fine. And we could see, for example, in this amplifier that's below us, the right channel spread between the lowest and the highest voltage. Essentially what we're doing here is we're essentially testing these v-fets to conduct these parameters. I rounded up the 177 to 180 because I'm using this bad boy over here, and I wanted to make sure that I don't go too much into the between radicals to measure. So I rounded up the 177 to 180. So this measurements right here may not be perfectly aligned with this chart for that reason. And but nonetheless, it's still more than good enough for one task at hand here. So what we're seeing here is between this bolded number right here, 17.2 volts, and 19.2 volts over here, we're seeing a spread of 2 volts. Again, these are different channels. So this is the J, it's a P channel, positive channel. So this would have a positive sign in front, and this is a K, it's an N channel. This would have a negative sign in front, which is this is voltage at the gate. So ignore the sign. We're just looking at the actual number. So this has a spread of 2 volts. And this guy right here has a spread of 1 volt. And if we look careful in here, within the same set of 12 VFETs, we could actually rearrange them to get a better, closer match. And that's exactly what I've done here. You could see how they move from one side to the other, crisscross them to be rearranged in a more optimal way within the same set of 12. So now we see on this channel we have only a spread of 0.8 volts from 2 volts. And actually, well, it's kind of cross. So this has been reduced from 2 volts to 1.4, and this from 1 to 0.8. So it's a success story. And what this actually means is now that within the same bank of 6 per unit, one VFET doesn't have to work as hard as it did before. That heat dissipation will be spread more evenly. In other words, for example, in this situation, if this VFET was essentially had to be, if you bias the entire set somewhere in the middle, this VFET right here will be working harder and heat up more than, let's say, this one. This one will be cruising, this one will be sweating. So now by reconfiguring them, you have a lower spreads, therefore they're not going to work as hard. And there's another example here that I have of a unit, of the next unit that I'm going to share with you. Not this one right here, not the one that, this one still has its VFETs, but as I mentioned, there are multiple units here, which I'll be sharing with you in a minute. This guy right here, the VFETs are still out. For example, when I take these things apart, I actually mark them. 1, 2, 3, 4, 5, 6 here, 7, 8, 9, 10, 11, 12. But you're seeing that these are all over the place right now. Like this is 1, 2 is here, 3 is here, 8 is here. The reason is I kind of did the same thing. I rearranged them to get a better set, because this unit right here was actually right at a minute, 2.5 volts at a limit. 2.5 volts spread. Here's a 16.7 volts, which actually looks like a rank 5 on a high end. And here is a 19.2, which is a rank 6 on a high end, according to the chart that I shared with you earlier. But as I mentioned to you, I'm not too worried about this being 16.7, which is lower than, I think the limit there says, this right here is rank 16.9 to 19.4 would be rank 6, and 14.4 to 16.9 would be rank 5. So this 16.7 here, and actually the one right here next to it, 16.6, look like a high rank 6. But as I mentioned to you, take my measurements because of the rounding up and because I'm using an analog instrument and it's my eyeballing those gradical, take that with a grain of salt. I'm not concerned about this at all. This is also an original set of VFETs, so they weren't mixed from different sets. Not that it matters, but the spread was at 2.5 volts. So I said, what can we do to make this better? And the other channels are 1.7, so this is not a trivial number either. So by rearranging them, taking the time to rearrange them, I actually was able to get even better results than I did with the other unit, with this other one right here. So this was actually the yield here was even more beneficial, because now we went to 1.4 and 1.5 versus 2.5 and 1.7. So again, this amp will work better than it did when it left the factory. Again, another example, besides all the other changes that we're making. All right, so I think this kind of ends my dive into the paperwork. And so what I'm going to do next, I'm going to take this out and I'm going to bring one more unit in here, which actually shows progress of between this one that has no work done and this one that is complete. So I will be right back. All right, what have we here? As I mentioned to you, I will bring out a unit where work is in progress. So essentially, most of the modules in most of the major components in here have been brought up to the stage where the work is complete. All I need to do to this amplifier is essentially get everything to work together to get it to the same stage as this guy. So let's walk through what you guys are seeing here. So first of all, the front end board, as I mentioned to you,
This guy right here has about 3 versions, and so this one has been brought up to the newest, has the newest changes. Additionally, I have eliminated the 8-volt rectifier and moved it to the power supply, which we're going to be talking about in a minute. I don't know if I mentioned to you this power supply board right here. It's quite involved. It looks small, but it's quite involved. It has about 7 voltage rails. Some are regulated, plus a pass-through for the AC lines, which come from the transformer, pass through this board and come and feed the AC to this secondary bridge rectifier right here, 48-volt regular power supply for this voltmeter. So this little board is quite involved, but I was able to get this right here plus everything on this board moved onto this new power supply assembly. And here we're using 2 very good audio grade capacitors, and we're actually able to exceed the performance of the original power supply. Now, a little bit of history. Back in the day, Luxman and Accuphase and others took power supply to a different level. They were very serious about mitigating some of the parasitic elements that Sony and Yamaha, for example, try to mitigate with the dual capacitors, and do it in a more elegant way without the need of using dual capacitors. And some of those lessons are we have to actually have essentially a balanced ground potential. We have to have symmetrical current paths in order for us to have ample supply of current that is balanced between the plus and minus rail. The center tap for this transformer is no longer connected directly to the center ground, and that creates that basically creates a balanced ground potential. And what's going on in here is a little dirty. I gotta clean that. Yeah, so anyway, so this everything fits in here. People are concerned like, oh, how am I going to fit? These are 63mm caps, so quite sizable, but they will fit just fine. Don't worry about that. The voltmeter will fit in here, no problem. But the space was a constraint, for a lack of better words, and for that reason I had to use a hybrid of SMD components and through-hole components, which you could see how this power supply looks like on this side, and a bunch of other components on this side. You could see the symmetry of the bridge there. You could see how close these rectifiers are now to the capacitors right in the back. These are actually soft recovery diodes, so they're also much more beefier, as are 15 amps a pop. So a 30 amp bridge, and they're soft recovery, which is very important because that means less ringing into the circuit when those diodes switch. And this is again a superior power supply to the original one. Another thing, just for reference, here's the dual cap, here's the power supply, and we had about we eliminated about 16 to 18 inches worth of wire length that was sitting between the capacitor and the rectifier. This may seem trivial, but it's actually, everything counts. All the small changes that I'm making here count. You will see that what we achieve is a very low noise floor for this amplifier, which wouldn't have been possible without multiple changes. And again, so now we have a modern state-of-the-art power supply with very, very good capacitors made for audio. A lot of improvements, as I mentioned to you, in the layout, the parts used, etc. So again, another what I would call better than new type of feature. Now it looks ugly. I experimented with different colors in here. I'm gonna change this to other colors, green or black, or in some point in the future, but yellow was good and easy to work with, and I thought it would be similar to this yellow, but the contrast is quite serious, so I don't know. The jury's still out on this. It's kind of clashing, but it is what it is. It works very well. Okay, so that's about the power supply. Again, let's come back in here. May repeat this again. If you replace components on these boards, try not to replace components based on the spec sheet of the old part. Try to focus on the function of the unit, of that component within the unit. And because if you're too focused on the specs of the old part, you may miss the opportunity to use components that are actually better suited for their job in the circuit, which are available, right? So that's what I'm doing here. Again, I hate shotgunning, so there are some components that we're changing here, as you could see. As I mentioned to you, change some of the transistors, some of the resistors, the trim pots, but not everything, right? Then this section was completely eliminated, and this board is brought up to the newest version. There, as I mentioned to you, there are 3 versions of these. The original JFS test, okay, I left them alone. Basically, this is how the board looks like. Yeah, so I still got to do the wire harness. Then this thing was cleaned once, but it will be cleaned again. One thing that you're noticing all of those connectors. These connectors are going bye-bye. I have been cutting a bunch of them off. You can see them right here. Actually, let me pick one up. I'll show you something. So I've been criticized in the past because I'm cutting off these components, these connectors. But what if it needs to be serviced? Well, first of all, I don't think this will need to be serviced anytime soon. But if it is, and my choice is between serviceability many decades from now, potentially, versus sustained reliability, I will take about 3 seconds to make that decision. And this is a good example. You see that greenish stuff in there? That's probably from some liquid that was put in there, some grease, some dielectric grease that was put in there for improved contact. But it looks like the brass of the pin is starting to react to that. It's not on all pins, so but that's all you need. It's 1 or 2 pins to be better. And if you're unlucky to have one that doesn't work here and it handles the bias current, you're pretty much done. You're killing your VFETs because of this stupid thing. So in the past, I cleaned them, I serviced them, I tried to reuse them, but I gave up on that idea. So wire to board it is. We'll talk about it more a little bit when we go and looking at this unit. So bottom line is that's what I'm doing. I'm snipping them off. Same thing with the speakers. Other things that we're doing in here, I separated the harness. This is the power switch for this unit right here. This is a US unit right here that you're seeing. These are the speaker cables that come to that front selector, which is right here. We're going to talk about in a second. And they used to run parallel to this AC lines and go all the way back to the speakers. So I'm separating them, essentially running them underneath 2 sheets of metal in here, so we have better EMI isolation. And so, as I mentioned to you, everything helps. And at the back here, I'm trying to do at best possible to separate the AC power lines from anything audio. The entire harness has to be redone. Obviously, I need new wiring for my changes. What you're looking at over there, is I'm going to look at it in a second. This is the new DC protection circuit, basically the Sony implementation, the Sony TAN-8550 implementation. You're seeing a little bit of this wires being a little longer because until I'm done, I'm using them to hook my clips to it, but at the end I'm cleaning this up a little bit more. This is the input circuit, which we're going to talk about it as well. These are the driver boards. I mentioned to you you see they're empty. A lighter amplifier is going to be faster, right? No, it's not a race car, but anyways, the crowbar protection circuit is gone. You're seeing here a mix of all the new components. As I mentioned to you, no shotgunning, but the critical components have been replaced. You are seeing there some beefed up carbon metal film resistors where it matters. You're looking at very good carbon film resistors right here. These are Iskra resistors. Very good for sound. They sit straight into the signal path. You're also seeing a carbon comp resistor here. The original was also a carbon comp. This is part of a low-pass filter, part of the Zobel network right at the output of the amp. I imagine the Sony engineers used a carbon comp in here, not because they ran out of different other type of resistors, but because these are non-inductive. And so I actually replaced the original one, not because it's bad. These carbon comp resistors are known to absorb moisture and drift over time. Out of all the Sony amplifiers that I worked on, none of these resistors were out of spec. But I changed them because in case the amplifier ever suffered isolation or will suffer isolation, they could be compromised. And I also changed the part of that low-pass filter, this capacitor right here. Even though these film capacitors are perfect, there's nothing wrong with them. No need to change these film capacitors. They're actually very good quality film capacitors. They would not fail. And very importantly, they have, I think, non-ferrous legs. So that's good. Most of the new capacitors have ferrous legs. This one here does not. right? Neither does neither do the legs of this resistor. So I paid special attention to that because I guess I'm assuming the reason Sony used this carbon comp resistor was to make sure they don't have any inductance there at the output. So this one is actually bigger in wattage, but the same value. And so that's why you have it there. And there was one more on the side, but I don't think that one makes so much of a difference if it's inductant or not, because it sits right across the Zobel coil. So I moved that in on this board right here, and you will see it when I get to that. So that again, kind of my approach to this is keep components that are known to be reliable, change the ones that are not reliable, change the ones that we have choices of better parts suited for the job, and leave it at that, right? This drain resistors right here, or source resistors, depending on the way your amp is configured. They would drift if the amplifier would have suffered some sort of a catastrophic failure on the output devices. This will actually either be shorted or much off their value, but these are not. I do have the same part brand new available. So if you measure this at the same temperature, new parts, they usually test the same. So keep that in mind. If you're testing this and you see them being drifted a little bit, don't hold them with your hand. Make sure you're testing them at a temperature based according to spec sheet. Otherwise, they will be off value in some cases, but so will the brand new parts. They're very temperature sensitive, so keep that in mind when you're looking at these resistors and deciding to replace them. All right, in a nutshell, that's what I've done here. Obviously, changed a bunch of Zeners. Those dead diodes I replaced. What else? Not much. All right, let's look at the front selector, which we have over here. We did look at the power supply, so let's move this guy out of the way. All right. Front selector, what I did, I hijacked the function of this first waffle right here, which handles input signal. Basically, it still works, but essentially what it does is turning on off the coils of this sealed relay right here, which now handles the on off for this potentiometer. So that's all this does essentially. This waffle right here basically says pot in the signal path, pot off the signal path, but it doesn't do it. The signal doesn't travel through those contacts. We now have DC, and it's I'm essentially doubling up those contacts. So basically we have redundancy of contact just to turn on this relay, and then the relay itself inside, it's essentially turning this on and off. So that's what we're doing here. Essentially, we're hijacking this. I put a header and mounting this in here. I'm going to get some power to it, and that's it. This is, again, cleaned up. And as I mentioned to you, I'm actually taking these things apart and cleaning them, then putting them back. You see this guy right here. It's pretty clean. Let's see if you could see it. That's clean. Clean. There you go. But it's supposed to clean the stuff. I'm not expecting a cookie for that. I did the same thing for this switch right here. You can see it's pretty nicely and clean. This usually gets a wire harness gets straight mounted into that, but in this case I'm going to solder to those pins directly. I don't want any kind of problems. I actually had to go over a unit that was recently restored by somebody else to correct some of these contacts because they're a pain in the ass to clean, and so it's not unusual that they actually are problematic. So anyways, that problem is solved. The switches right now, all their switching is actually DC, and again I'm doubling up the contacts in here, so now we have twice the contact, and it switches DC versus low level signal. So this will never die. Essentially, you never need to clean them. All right, what else? Here is the, let's talk about, let me put my camera on something, 1 second. All right, so let's look at this assembly. So this is how the speaker's assembly looks like at the rear. So basically, actually it sits, yeah, like this, and it's mounted directly, the speaker protection is mounted directly into the speaker post. This replaces this type of speaker post. So now what you're seeing here, if you're like, what the heck, how did you get this to work? Because these are full-size speaker posts. These are not the mini speaker posts anymore. These are actually inspired by the by a different major brand. I'm not going to name them here, but in my view, they're much better than the original style they're copying. Very good speaker posts, real solid. I did choose a plastic exterior because they're still quite tied to each other, so kind of prevent any type of cross wiring in here. But this is how they look. These are reusable for all first generation Sonys. So I made this modular where now they will fit in the 8650, 5650, 5550, 4650, and obviously in this amplifier right here, the 8550. They will be replacing this style of speaker posts. And putting this aside, and this is essentially a combination of the TAN-8550 protection circuit, plus I move part of the Zovo network from the output from the driver boards to this section right here. This gets mounted like this. Space is very tight, so this had to be very compact to fit in there. You'll see in a minute. Actually, this can also be used in the 8650, which suffers of the same crowbar protection or lack of protection circuit problem. And the space in 8550 it's tight, the space in 8650 it's even tighter, but this will fit in there. So this is how she looks. Gets mounted, as I showed to you, directly on the back of the amp right there. And as I mentioned, also the some of those end of the wires are there like that right now because this gets first tested. I need to test these driver boards without VFETs. And by the way, if you're doing that, you need to test the voltage at the gate. Yeah, you could test it across the resistor as the manual says, but you must test them at the gate. Make sure you have gate voltage. Make sure is enough to be higher than the pinch off voltage of the VFET rank that you have. You got to verify that, and you got to verify that it's adjustable. Otherwise, don't put your VFETs in here before you try. There are ways to test that, right? The DC balance should be adjustable right away. So that should work. So you cannot put VFETs in this amplifier before you make sure this driver boards work, because mistakes happen and you could kill your VFETs. Anyhow, just want to say that. But for that, I'm hooking up wires to this ends that I'm leaving here. Then I'm trimming everything more or less when I'm completely done with the unit. All right, let's talk about this side, because what you're seeing here right now, it's essentially a replacement for this rear input board. There are a couple of switches here that I have to pull out because I'm reusing. I should have turned one of these amplifiers around. Let's talk about this a little bit. So what you're seeing here is input 1 and input 2, left and right. You will see that in the back. And we have a couple of switches in here. This couple of switches are actually allowing us to switch between coupled and decoupled for each channel individuals. Couple and decouple means you could take the signal via this capacitors, which is essentially a subsonic filter, essentially a rumble filter called by other companies, but it's a subsonic filter. Cuts off the bottom, actually below 20 hertz, I think, the bottom of the frequency range. And these are this type of switches right here, which you're seeing on the replacement board. These are, again, they are open to air switches, so they're prone to contact degradation over time. And signal travels to them either in on and off position at all times. So we have to manage that, and we're managing it with help of sealed relays as well, right? So we're running the signal through here. So essentially, and here's the coupling caps that we're using, a little bit better grade. These are polypropylene, so they never need to be changed. Neither do these, but they're a little bit bumped up in value. So the this actually will allow lower frequencies to pass through them. They're 1 microfarad versus 220 nanos. Anyhow, non-consequential anyways, because these are fine too. And you could run, you see what it says there, test and test the normal. That's exactly what it says in the back of the amplifier, which we'll see in a minute. Test means you're bypassing these caps, so basically going from this input RCAs all the way to, actually you're going, unfortunately, you're going from here all the way back to the front, going through this relay right here now, before you were going straight to this open to air contacts. From here, you're coming into the input, pull these suckers out, to the input section of this board, and from here you're going out through the amplifier sections. So it's kind of quite a zigzag, and you would be passing through a lot of open to air contacts, which is what somebody needs to address immediately. If you're working in one of these amps where you're going through the extent of the work that I've done here or not, you got to figure out a way to manage these, right? Either cleaning them or whatever you're doing with them, bypassing them, wherever your choice is. I wanted to keep everything functional, so no bypassing. Bypassing is not a choice. My choice is to use these guys, which will work for many decades. They'll never be needing service, at least at the duty they are going to be employed to do work here, right? And I'm always choosing like the rest to be the most used function, which is test function. In this case would be bypassing the caps. You know, I think under address they are set to do that. And this relay in the center right here essentially switches between, it's essentially a switch, this switch right here, this switch right now, instead of switching the actual signal routed through this, as I showed you earlier, open to air switches, all it does is switches the relay on and off, this guy right here in the center. And what this guy does essentially either allows you to go input 1 or input 2 in the back, or whatever, whichever one it is. But I think they're reversed, so I think this is input 1 and this is input 2. Anyhow, and we're also beefing up the RCAs. We're no longer using these RCAs, but we have to keep in mind that the level of the switch right here with the level of this plate has to be even. You could see there's some spacing in there that's being accounted for in the original assembly. So the way I'm accomplishing this, it's with a sub-assembly. So basically what we have here is this insert. Basically this is the first assembly of the RCA. This gets mounted into the case, then mounting the switches, and you're putting this through it, and then you solder in the back. And now basically what you have that perfect spacing, and you never have to worry about having uneven and cocked boards, etc. So this board isn't finished. This one is finished right here. This one still dirty because I still got to solder, and then everything gets clean on the end once I put in all the switches and everything. This switches, by the way, they're a little taller than the original Sony's. This toggle is a little taller. These are B1 style switches. The Sony ones are a little shorter, but I have this here for exhibition purpose because the ones for this board are still in the unit. So this is just the board that I made ahead of time. Basically the ones from this unit are in here already, from the original unit that are in here, and the ones from here are already in. So this kind of gives you an idea. Of course, all the changes, as I mentioned, make sense. You could see the wire harness here is being routed. I no longer needed to use this wire harness, not that because it wasn't good or anything, because it uses connectors, and because a lot of this has been altered. It works, the functionality is different, it gets the same results, but functionality is different. What I'm using instead, I'm using, for example, Mogami shielded cable for signal wires. So this is a really good, flexible, oxygen-free copper. No complaints about it. And then I have a lot of power cables, which are actually silicone wire that handle the DC between all these assemblies here. The ground layout management has to be retained. Sony was very careful on retaining or actually ensuring there are no ground loops in here. And if you're not paying attention to that, ground loops will happen. Okay, enough about this unit. You kind of get an idea of the amount of work. Obviously, a lot of research went in. Obviously, I didn't get everything right from the beginning. A lot of iterations happen. Many months of iterative progress, but here I am, and these things work beautifully together. Again, as I mentioned, these are 3 of the amplifiers. What I'm going to do right now, I'm going to turn them with the back, so we could talk a little bit about the back of them and kind of show you how the connectors look like. And also I want to show you, because what I have here in the house, as I said to you, I have this European model here, and both of these are US models. Then I have a Japanese model in here, and we're going to go through that. So I kind of show you the small minor differences between the 3 different types, and kind of how they look and what I had to do in there. So I will be right back once these things, I clean out bench and I turn these things around. I'm also then after that, I'm going to take the top off of this baby and we're going to look at how the finished configuration looks like. I'll be right back. All right, here we have more units. I couldn't fit more than 4 on a bench, but this is enough. We have all varieties here. We have an EU model here. These are US models, but this is a before and after, and this is a Japanese model. So I'll briefly share with you how the back of these guys look like, and some of the particularities, mild differences between the different region where these amplifiers were sold. This is a US model, all original. This is how it looks with this kind of power switches. I'm sorry, speaker. They look like switches. Speaker posts. This is how the original inputs look like. The switches that I talked to you about. Again, normal and test. Input 1 and 2. This is a serial number. You could see right there. It starts with 8. It is indicative of a US model pros. The AC120 is printed directly on a sticker. Japanese and US models did use a power cord like this, and they have this unswitched AC outlet, which no one is using. But unfortunately, the artwork is printed there, so you will see why I'm not putting my IEC connector in there. And here's the unit that you saw earlier. This is the back of it, and you kind of see how everything looks right now that is replaced. So again, the switches, as I mentioned to you, now have a different function, and new RCAs, new speaker post that you saw, and I have an IEC connector in here. Now, if you noticed, right next to this cord, there's a sticker, and that sticker, unfortunately, it's in the most optimal location for that new IEC connector, and so it has to be moved up here to be able to put the IEC connector at this location. This is the ideal location because otherwise you end up with a hole. You have to put a plug on it, and the surface isn't even. The plug looks like crap. So ideally you put the IEC in here. If you put it in here, you can, but it's going to screw up this entire area. So it looks amateurish. So my decision is to put the IEC in here, even though it takes a little bit more work because I have to move this up. That's exactly what I did here. So you could see this sticker is moved up. Now pay attention, if you see the sticker peel, that's exactly how it was. This is not a scratch. That's actually, well, maybe it is a scratch, but it was there before, and it's not as a result. This one is not a scratch. It's one of those creases in the paint that you see once in a while on this amps. So here's the IEC connector. This has 2 prongs only, just like this one right here, because this is a 2-prong cord. The ground main there was not connected to the chassis ground. And you could see I moved the sticker over here. You see the 8000 serial number and the AC 120 volts. This is how a US unit will look. What else? Let's go to the Japanese unit. Japanese units are very similar to the US units in terms of having a cord here. For this one, I also had to move the sticker up. Because it's a Japanese unit, the serial number starts with 2000 and it said 100 volts in there. So I had to apply that AC 120 volt sticker. All of these units can be converted. They have a voltage selector, so you could use them either in Europe or here. So no worries about from which region your unit comes. They all could be adapted to the local power supply, basically mains power. So this is the JP unit. Again, have to move the sticker up to get the IC in the location of the cord. All right, that's the US unit. Here's the one that's a little bit more different for a couple of reasons. So first of all, for the European models, they all came with an IEC built in, so less work there. But the mains earth was connected to chassis. That presents a problem because you're importing all the junk in all the noises in your mains into your unit. So I wasn't going to replace this IEC connector with one with 2 prongs. I'm going to leave the unit as original, but what I did, I added a filter on this ground pin that looks like that. This being a European or international model, the serial number starts with 4, and you could see that the AC is marked for 100, 120, 220, 240, 50 or 60 hertz. and it has a obviously a selector there, which that looks unclear right now because it's dusty, but it's actually transparent. It's my lighting here that's pretty bad. Controlling the lighting here is quite difficult, but yeah, otherwise it's the same. So I didn't have to move the sticker there because I don't have to cut any power cords, so that's the easy part. The extra thing that I had to do is to make sure I have a filter on the pins, so otherwise I don't bring in the junk from the mains into the unit. But that's it. This is how they all look. The speaker posts are really a major plus. Now everybody could use either bananas. You could still put bare wire in there. You could use spades, which spades are probably my favorites. So yeah, really nice, very usable. As I mentioned to you, these are now not just working as new, but function as new. All this modern functionality brings them up, takes out some of the functional obsolescence that is built into some of these units. Not all of it, like we talked about the front selector between the multiple sets of speakers. I mean, modern amplifier will probably only have one of these sets, but at least we could use more better quality connectors, both at the input and at the output. Okay, so that's it for the back of these amps. What I'm going to do next, I'm going to turn this guy around. I'm going to clean my bench a little bit, or maybe leave him there. Turn this guy around, pop the hood so I could show you how everything fits in together on a final configuration. All right, here she is with the top open, all fitting together. You could see how nicely this power supply fits right now with the voltmeter. No issues here. I was able to fit 63 millimeter diameter caps, no problem. Chimneys are back, as I mentioned to you. Do not block these chimneys if you love your amplifier. From board right here, you could see the missing power supply, the 8-volt regulator power supply, which moved here right now. You could see all the replaced components that I called out. Again, didn't shotgun this board, didn't need to, but critical components were replaced. There are some improvements that can be done here over the old circuit. This again has all the actual upgrades. This is the latest version essentially compared to other. So as I mentioned, there are 3 different versions of this board, so you must do the updates for the amplifier to work correctly. These were done by Sony. This one right here, yes, this one right here has done at the factory. So this is like the latest version. So I don't need to do anything to this one. But I think I may have done changes to the other one. Anyways, doesn't matter. There are changes that should be done for this to have the latest version. The ICs looking dual JFETs right there work perfectly. DC balance is very stable of this amplifier. You could see the missing crowbar protection circuit there and there. And as a matter of fact, why don't we do this? Let's power this puppy up and let's listen for the click of the relays at the back. Boom, did you hear that? You just heard the first 8550 with a with a speaker protection that is run by time delay and relays versus the crowbar. Let's do that again. I get a kick of this every time. Let's do 3 seconds and we should hear something. Boom, there you go. Very, very nice. Let me turn this off before I zap myself because I put my hands all over here. All right, so yeah, that's that. So that crowbar went away. We got a what is now very much a standard DC protection circuit with relays and time delay. Wire to board, again, I mentioned this to you earlier. This is not a recommendation for everybody to do that. I'm just saying this is my way. I'm not saying your way is different or better. I mean, your different way of doing this is worse than what I did here, but I have very specific reasons why I didn't do this differently. You know, there are other ways of doing this. Obviously, you could change the headers, put screw to board, use those posts essentially that are used heavily in the defense and aviation industry for their electronics. You could use any of those options. I'm just going to say that to me this is the most rational way of doing this. And as I said, if it's between choosing between the serviceability versus the reliability, sustained reliability of this unit for me, in that case, there's almost no debate there. So some technician that may potentially come in here years from now may cuss me out for a few minutes, but if they know what they're doing, they have proper tools and knowledge, this will not be a deterrent. This is actually very serviceable. You could imagine there are multiple iterations of things that I've done to these amplifiers, and I didn't get it right from the very beginning. So I did have to essentially go back and forth with these boards being fully wired in to do tests, changes, etc., etc. You know, as I mentioned to you, this takes months and months and months of testing and working and changing different things. So what I'm trying to say, these are accessible. It's not that hard to access them if you have the proper tools and knowledge. So this may actually be good because it may deter some Yahoo going in there and monkeying around and ruining the unit for whatever reason. So maybe that's going to deter someone that shouldn't be in here to begin with. So, hey, I'm trying to find out a positive. But anyway, so here we are. We are kind of at the end of this video. What else can we talk about? Okay, that space right there is essentially very tight. It is essentially a pain in the butt to manage. Obviously, this wasn't an easy fit or accomplishment. This is why this board is so tight and compact. This actually, as I mentioned to you, works with the 8650, which has even less space than the 8550. You could see a piece of aramid fiber paper right there. I think the brand is Nomex. That's a fiber reinforced paper. You could put a torch on it. It will not burn. And you could see I have a couple of drops of high temperature silicone holding it back, sticking it to the chimney. The reason I put that there is just my OCD paranoia, thinking that this may be hit. This thing may be hit and bend during either shipping, and somebody would power up without knowing, or actually while working gets dropped or something. Again, very far away edge case, probably will never happen. But yeah, you could see the speaker space between the chimney and the speaker post is no larger, no smaller than what it is with the in the original configuration. So it's very tight in there. You could see, and then if it is if this was an 8650, it would be even tighter. Same kind of story goes for the for this board right here. You could see how the capacitor protrudes on both sides of that input board. The reason being is that obviously there's very little space in here between the back of this plate and this board. So if I put a capacitor in there, it barely fits. So if I want to use a bigger diameter capacitor, I could use now the entire width here between this plate all the way to this plate without the worry of the actual PCB dividing the space in between, which is already very tight. So that's why I have that perforation. The PCB now, the capacitor could be of different diameter. All right, a lot of details. Obviously, you realize that this level of work requires a lot of time, and that may not be feasible if you're just doing only one of these amplifiers. I have a few of this. I think I have about 4 of my own, I think. Maybe 3 or 4 of my own, I forgot. And I have some 8650s. But then I have friends that have these. And I also have other people that reached out to me that they want theirs. As I mentioned to you, the owner of this amplifier actually has a few of them. This is the second with this configuration that he will be receiving. Again, this is done for a while right now. I tested heavily in my listening room and kept the hostage a little bit more. It should have been out of the door 2 days ago. I kept the hostage just for me to shoot this video to share with you guys and accompany the rest of the units. So what we're gonna do next, I'm going to, because this video is already really long, you hear me rushing through. What I'm gonna do is essentially put a pause on this, and I'm gonna share with you a couple of screenshots of the some bench tests. I'm not gonna have enough time to go through a full set of bench tests now, because this unit needs to go, and this video is already very long. Full set of bench tests requires some time. Ideally, we would be comparing it to a original unit. I do have another unit, a mule, which I call it a mule, which is essentially a unit that works to factory spec, tested, very stable. What I usually do, if you watch my other videos, actually, when I go through these components and I replace all components that are known to fail, generally I look for ones that are still within spec, original spec of the factory. I take them, collect them, and make one mule unit that works per factory specs, works perfectly with all original components. Obviously, things like switches and connectors, those, I make sure that they work, either cut them off or whatever. But as far as the circuit goes, bulk capacitors, etc. This the my mule unit, which is not here, but it's very similar to this. It's unaltered essentially, other than making sure the circuit works, is my frame of reference. That's how I know if the changes I make are actually adding value or not. Obviously, in terms of reliability, that is easier to measure. But in terms of sound quality, as I mentioned to you, major changes such as working around the power supply or any changes to the amplifier sections, we have about 10 to 1 chances to make this amplifier sound worse than make it sound better. So anyways, that's my soapbox. As I said, right now I'm going to share with you some bench tests. My focus is not going to be on THD, for example, which THD should be expected to be very low because we went through all that v-fet rematching. All the transistors that I'm changing here are checked and matched. So THD is expected to be very low. That's not my curiosity, or where my curiosity will be focused on is the N factor. And sneak peek onto that, I've obviously tested this unit because it has to go to its owner. The N factor, the THD plus N, it's extremely low. And again, the click of the relays and all these other changes make it a TAN-8550 MKII. All right, I'll be right back with those screenshots, and then I'll end this video after that. All right, so I'm squeezing in a few snippets from my bench test of the amplifier that I just completed. This is THD, just for reference. We knew it's going to be really low, 0.002% or so. Typical dominant on the lower harmonics, the H2 and H3 dominant, that's typical for a v-fet. But what we're interested in is actually a THD plus N, which is here, which we can see the N factor only adds about 0.001%. Again, testing at the same parameters, around 10 watts into an 8 ohm load. This shows that this amplifier has a very low noise floor. I did also go and run a sweep between 10 hertz and 100 kilohertz, just for kicks. I'm supposed to see around anywhere between no more than a 3 dBs drop over the entire frequency band. I mean, over this frequency band, but I'm seeing less than 1 dB drop, so that's really good. The amplifier is solid, performs well. I didn't mention to you, but it actually taps out at about 130 watts. It's rated at 110, taps out at 130 watts. And we are at the end. We're way past the hour. We're definitely going to do a more in-depth bench test on this amps, comparing it old versus new. But that will take too long to squeeze in this one video. Again, we're way past this hour. I'm not sure how many of you are still hanging till the end. If you are here right now, thank you. Please don't hesitate to leave comments, questions, any type of observations you may have. It is highly likely that I will do a full write-up on this work and publish it on the solid state forum of the AudioKarma. Highly likely. Thank you all for watching. We'll talk to you the next time.